Alright, let's go. Number 10. Titan's complex organic chemistry. In 2017, scientists analyzing data from NASA's Cassini spacecraft made a startling discovery in the atmosphere of Titan, Saturn's largest moon. The spacecraft, which had spent 13 years studying the Saturnian system before its mission ended on September 15, 2017, detected complex organic molecules suspended in Titan's thick, hazy atmosphere. Molecules so intricate they resembled the chemical building blocks that preceded life on Earth. Among the exotic compounds floating in those orange skies was cyclopropanylidene, a carbon-based molecule never before detected in any planetary atmosphere. What made this discovery particularly remarkable was Titan's environment. Scientists had long known that Titan possessed a nitrogen-rich atmosphere remarkably similar to early Earth's, along with liquid methane lakes covering its frozen surface. But the moon's surface temperature hovers around negative 290 degrees Fahrenheit, an environment so hostile that conventional chemistry should barely function. The expectation was simple molecules, not the elaborate organic compounds Cassini detected. The molecules shouldn't form naturally in Titan's frigid conditions. Yet there they were, being continuously synthesized through processes scientists still don't fully understand. The chemistry included complex organic compounds called tholins, which create Titan's distinctive orange haze and bear an unsettling resemblance to the prebiotic chemistry that may have existed on Earth before life emerged. Analysis revealed that radiation from the sun was driving reactions in the upper atmosphere, creating molecules of increasing complexity as they drifted downward through the haze. Researchers proposed that Titan's methane lakes might harbor exotic life forms, using liquid methane as a solvent instead of water, operating on entirely alien biochemistry. The presence of these complex organics strengthens that possibility, suggesting that the chemical foundation for some form of life might already exist. Other scientists theorized that Titan represents a frozen snapshot of what Earth looked like billions of years ago, before biology transformed our planet. The implications are profound. If life can arise using methane instead of water, operating at temperatures that would instantly freeze everything we know as living, then the number of potentially habitable worlds in the universe expands dramatically, beyond the narrow constraints we've traditionally imagined. Number 9. Przybylski's star chemical anomalies. In 1961, Polish-Australian astronomer Antoni Przybylski turned his telescope toward a faint star in the constellation Centaurus and discovered something that defied every model of stellar physics. The star, cataloged as HD 101065 and located approximately 410 light-years from Earth, displayed a spectrum unlike anything seen before. Its light revealed impossible concentrations of short-lived radioactive elements, including technetium-99 with a half-life of just 211,000 years, and spectral signatures suggesting the presence of plutonium and other heavy actinides that should have decayed billions of years ago. Stars are nuclear furnaces that create elements through fusion, following well-understood pathways of nucleosynthesis. While massive stars can produce heavy elements in their cores, the radioactive isotopes detected in Przybylski's star should not exist in such concentrations. Technetium, for instance, has no stable isotopes and decays relatively quickly on astronomical timescales. Any technetium formed when the star was born should have vanished long ago. Yet there it was, its distinctive spectral lines unmistakable in the star's light. What makes the anomaly truly bizarre is the apparent absence of hydrogen and helium in the star's spectrum. These are the most abundant elements in the universe, the primary constituents of every normal star. A star without detectable hydrogen or helium shouldn't exist according to stellar physics, yet Przybylski's star shows no signs of either. Instead, its outer layers appear dominated by rare earth elements and radioactive heavy metals in concentrations that make no astrophysical sense. Scientists have proposed exotic explanations. Perhaps the star's intense magnetic field dredges up heavy elements from deep within its interior, temporarily concentrating them in visible layers. Maybe it absorbed a planet rich in unusual elements, though this fails to explain the radioactive isotopes. Some researchers have even suggested, half seriously, that the star might be contaminated with nuclear waste from an advanced civilization, though most astronomers favor undiscovered natural processes. Przybylski's star remains unique among billions of stars we've observed. If this is simply exotic stellar chemistry we've never encountered, why haven't we found a single other example? And if it isn't natural, what kind of civilization would possess the capability and motivation to seed a star with radioactive elements visible from hundreds of light years away? Number 8. Mars methane seasonal variations. On June 19, 2013, NASA's Curiosity rover, which had landed in Gale Crater less than a year earlier, on August 6, 2012, detected something in the thin Martian atmosphere that made astrobiologists reconsider everything they thought they knew about the red planet. Methane levels spiked to 7 parts per billion, 10 times higher than background levels, then remained elevated for weeks before mysteriously disappearing. This wasn't a measurement error or contamination from the rover itself. Something on Mars was actively producing methane. Scientists had long assumed Mars was geologically dead, its interior cooled and solidified, its surface transformed into a frozen desert billions of years ago. While trace amounts of methane had been tentatively detected before, they were dismissed as measurement artifacts or residual gas from ancient geological activity. The 2013 spike changed everything because it was sustained, significant, and most importantly, it wasn't an isolated event. Follow-up observations revealed that methane concentrations fluctuated with Mars's seasons, peaking during late northern summer. On Earth, approximately 90% of atmospheric methane comes from biological sources, produced by microorganisms living in oxygen-free environments. The remaining fraction comes from geological processes like serpentinization, where water reacts with iron-rich rocks deep underground. Mars could theoretically produce methane geologically, but the seasonal variation pattern suggests something responding to environmental changes, something active right now beneath the planet's surface. The European Space Agency's Trace Gas Orbiter, designed specifically to map Martian methane, added another layer to the mystery when it detected methane plumes in 2019. The gas appears and disappears far more rapidly than Mars's thin atmosphere should allow, suggesting some unknown mechanism is both producing and removing it. Scientists propose theories ranging from subsurface bacteria releasing methane seasonally to previously unknown photochemical reactions in the soil, but none fully explain the observations. Mars is not the dead world we believed it to be. Whether the methane comes from microbes living in subsurface aquifers or from geological processes we don't yet understand, something on our neighboring planet has been actively producing this gas for at least the past decade, and the seasonal pattern suggests it's still happening right now. Number 7. Enceladus hydrothermal vent. Evidence. In 2005, NASA's Cassini spacecraft detected towering plumes of water vapor and ice crystals erupting from the south polar region of Enceladus, Saturn's tiny moon, just 310 miles in diameter. These geysers shot hundreds of miles into space from mysterious cracks in the moon's frozen surface, carrying with them something scientists never expected to find on a world so small and distant from the sun. Chemical analysis revealed not just water, but organic molecules, salts, and molecular hydrogen, the exact cocktail of chemicals associated with hydrothermal vents on Earth's ocean floor, where entire ecosystems thrive in absolute darkness without a trace of sunlight. Enceladus should have been geologically dead. Moons that small typically freeze solid shortly after formation, their interiors too diminished to generate heat. Scientists expected a lifeless ice ball, perhaps cratered and inert like so many other small moons throughout the solar system. Instead, Cassini found an active world with a subsurface ocean estimated to be 6 miles deep, hidden beneath 10 miles of ice, kept liquid by tidal heating as Saturn's gravity continually flexes the tiny moon. On April 13, 2017, Cassini made a daring dive through one of the plumes and detected molecular hydrogen. This was the breakthrough that changed everything. Molecular hydrogen doesn't last long in space. It reacts quickly with other compounds or escapes into the vacuum. Its presence in the plumes means it's being continuously produced, and there's only one known source: hydrothermal vents, where superheated water erupts from rocky seafloor, reaching temperatures around 194 degrees Fahrenheit. The chemistry is identical to Earth's deep ocean vents, where chemosynthetic bacteria convert hydrogen and carbon dioxide into energy, forming the base of complex food webs that include shrimp, tube worms, and other organisms. The implications are staggering. Enceladus has liquid water, organic compounds, and a chemical energy source, everything necessary for life as we know it. The moon has likely possessed these conditions for billions of years, providing ample time for biology to emerge and evolve in that dark ocean. Unlike Mars or Europa, we don't need to drill through miles of ice to access Enceladus's ocean. The moon helpfully ejects samples directly into space. If microorganisms evolved in Enceladus's sunless ocean, they would represent an entirely independent origin of life, proving that biology isn't unique to Earth, but emerges wherever conditions permit, even in the frozen darkness of the outer solar system. Number 6. Europa's subsurface ocean oxygen production. Jupiter's moon. Europa has long captured scientific imagination with its subsurface ocean containing twice the water volume of all Earth's oceans combined. But recent discoveries have elevated this frozen world from merely intriguing to genuinely promising as a potential harbor for life. Analysis of data from NASA's Juno spacecraft combined with reanalysis of decades-old Galileo mission observations from the 1990s revealed something remarkable. Europa's ocean is being continuously supplied provide, with approximately 1,000 tons of oxygen every single day. This isn't ancient oxygen trapped in primordial ice. It's being actively generated right now through radiation chemistry as Jupiter's ferocious magnetic field bombards the moon's frozen surface. Scientists had long known Europa possessed a vast ocean beneath its icy shell, kept liquid by the same tidal heating that warms Enceladus. Early estimates suggested minimal oxygen production, perhaps a few pounds per day slowly accumulating over billions of years. The new calculations revealed production at a scale thousands of times greater than previously believed. Jupiter's radiation splits water molecules at the surface, creating oxygen that then finds its way down through cracks and fissures into the liquid ocean below. The discovery transforms our understanding of Europa's habitability. Oxygen is one of the most versatile electron acceptors in biochemistry, enabling efficient energy production in organisms. On Earth, the transition from anaerobic to aerobic life fundamentally changed the biosphere, allowing complex, multicellular organisms to evolve. Europa's ocean has been accumulating oxygen for potentially 4 billion years, while remaining protected beneath 10 to 15 miles of ice that shields the ocean from Jupiter's deadly radiation. Combined with probable hydrothermal vents on the seafloor providing chemical energy and nutrients, Europa possesses every ingredient necessary for not just microbial life, but potentially complex organisms. The ocean is stable, ancient, and energetically rich. NASA's Europa Clipper mission, launched on October 14, 2024, will conduct detailed surveys of the moon's ice shell and plume composition, potentially detecting biosignatures if they exist. An ocean containing twice Earth's water, continuously supplied with oxygen for billions of years, with chemical energy from the seafloor and protection from radiation beneath miles of ice. Europa stands as perhaps the single most promising location in our solar system to find life that exists right now, waiting to be discovered. Number 5. TRAPPIST-1 habitable zone discoveries. On February 22, 2017, astronomers announced one of the most significant exoplanet discoveries in history, fundamentally altering our perception of how common potentially habitable worlds might be throughout the galaxy. The TRAPPIST-1 system, located just 40 light-years from Earth in the constellation Aquarius, contains 7 Earth-sized planets orbiting a single ultra-cool dwarf star with only 9% of our Sun's mass. 3 of these worlds, TRAPPIST-1, E, F, and G, orbit directly within the habitable zone where temperatures could allow liquid water to exist on their surfaces. But what makes this system truly extraordinary is the planet's proximity to each other. If you stood on one, the others would appear larger in the sky than our moon, close enough to see atmospheric features, and possibly even weather patterns on neighboring worlds. Astronomers had discovered individual potentially habitable exoplanets before, but finding 3 in a single system was unprecedented. The implications for astrobiology extended far beyond simple statistics. The planets orbit so close together that material ejected from one world by asteroid impacts could reach another within years, rather than the millions of years required for panspermia between planets in our solar system. This creates a scenario never before observed. If life emerged on any one of these worlds, it could seed all 3, establishing the first known interconnected biosphere, spanning multiple planets. The system's star adds another layer of intrigue. Ultra-cool dwarfs burn their fuel so slowly they can remain stable for trillions of years, vastly longer than our Sun's 10 billion year lifespan. The TRAPPIST-1 planets could remain habitable for timescales that dwarf Earth's entire history, providing extraordinary temporal opportunities for life to emerge, evolve, and potentially develop complexity. The planets are also tidally locked, with one side permanently facing their star and the other in eternal darkness, creating potential terminator zones, where twilight conditions might prove ideal for biology. Follow-up observations using the James Webb Space Telescope have begun characterizing these worlds' atmospheres, searching for biosignature gases like oxygen, methane, or more exotic compounds that might indicate biological activity. The proximity of the system makes such observations possible with current technology, something impossible for most exoplanets. TRAPPIST-1 represents a fundamental shift in how we think about habitable worlds, not as rare cosmic accidents, but as potentially abundant systems where multiple Earth-like planets might simultaneously harbor life, possibly sharing genetic heritage across worlds, while we remain alone in our solar system with every planet barren except one. Number 4. The BLC-1 signal from Proxima Centauri. In April 2019, the Parkes Radio Telescope in Australia, part of the Breakthrough Listen initiative searching for signs of extraterrestrial intelligence detected a radio signal that perfectly matched what scientists had theorized an alien technosignature would look like. The signal, designated Breakthrough Listen Candidate 1, appeared to originate from the direction of Proxima Centauri, the closest star to our solar system at just 4.24 light-years away. What made BLC-1 extraordinary wasn't just its narrowband emission at 982.002 MHz, but how it behaved. The frequency drifted over time in exactly the pattern expected from a transmitter on a planet rotating and orbiting its star. Natural radio sources in space are typically broadband, spreading their energy across wide frequency ranges. Artificial signals, like those from Earth satellites and transmitters, concentrate their power into narrow bands for efficiency. BLC-1 was remarkably narrow, suggesting a deliberate, focused transmission rather than random cosmic noise. The frequency drift was equally compelling. As a planet rotates and orbits, the Doppler effect shifts the wavelength of any transmission from its surface, creating a characteristic pattern. BLC-1 showed precisely this signature. Follow-up observations intensified during December 2019 and January 2020 as astronomers worked to rule out terrestrial interference. The signal passed several critical tests. It appeared only when the telescope pointed toward Proxima Centauri and vanished when aimed elsewhere. Exactly what you'd expect from a genuine extraterrestrial source. Proxima Centauri hosts Proxima b, a confirmed Earth-sized planet, orbiting within the habitable zone where liquid water could exist. The possibility that humanity had detected a signal from a planet around our nearest stellar neighbor created unprecedented excitement in the CD community. For months, BLC-1 remained the strongest candidate for an alien technosignature detected in decades of searching. But in October 2021, exhaustive analysis finally identified the source: human-generated radio frequency interference, likely from malfunctioning electronics near the telescope. The signal was terrestrial, not alien, yet the episode revealed something profound. Random human interference could perfectly mimic every expected characteristic of an alien transmission from our nearest neighboring star system, demonstrating how agonizingly difficult the search for extraterrestrial intelligence truly is, and how easily we might dismiss or overlook actual contact signals hidden within the noise of our own technology. Number 3. K2-18b Biosignature molecules. On September 11, 2023, astronomers using the James Webb Space Telescope announced a discovery that sent shockwaves through the astrobiology community and marked a potential turning point in humanity's search for life beyond Earth. The exoplanet K2-18b, located 120 light-years away in the constellation Leo, showed tentative evidence of dimethyl sulfide in its atmosphere, a molecule that on Earth is produced almost exclusively by living organisms, specifically phytoplankton in our oceans. This represented the first time a potential biosignature gas had been detected in the atmosphere of a planet outside our solar system. K2-18b is classified as a Haitian world, a recently proposed category of potentially habitable planet with a hydrogen-rich atmosphere overlying a liquid water ocean. The planet measures 2.6 times Earth's radius with 8.6 times Earth's mass, orbiting an M-dwarf star in the habitable zone, where temperatures permit liquid water. The James Webb Space Telescope's unprecedented sensitivity allowed astronomers to analyze starlight filtered through K2-18b's atmosphere as the planet transited its star, revealing the chemical fingerprints of multiple molecules including methane, carbon dioxide, and water vapor. Dimethyl sulfide is the crucial discovery. On Earth, this molecule is created when phytoplankton break down dimethyl sulfonopropionate in seawater, and it's responsible for the characteristic smell of the ocean. No known geological process produces DMS efficiently at significant concentrations. While scientists emphasize that the detection requires confirmation and that theoretically some exotic non-biological chemistry might produce trace amounts, the molecule's presence on a world with a confirmed water ocean raises an unavoidable question. Could we be detecting the atmospheric signature of an alien biosphere? The discovery's significance extends beyond K2-18b itself. The James Webb Space Telescope achieved this detection in its first year of operation, analyzing just one of thousands of known exoplanets. If biosignature molecules can be detected at 120 light-years with current technology, the implication is staggering. We now possess the capability to potentially discover life on other worlds, not through direct contact, but through atmospheric chemistry. The tentative DMS signal on K2-18b might be the first glimpse of what we've searched for throughout human history, proof that life exists beyond Earth, written in the chemical composition of a distant world sky, waiting for us to develop the instruments sensitive enough to read it. Number 2. Cumulative exoplanet habitability statistics. When NASA launched the Kepler Space Telescope on March 6, 2009, astronomers hoped to answer a fundamental question: how common are planets in our galaxy? The spacecraft stared at a single patch of sky containing approximately 150,000 stars, measuring tiny dips in brightness caused by planets crossing crossing in front of their stars. When the mission concluded on October 30th, 2018, Kepler had discovered 2,662 confirmed exoplanets and identified thousands of additional candidates. Statistical analysis of this data produced a conclusion that fundamentally transformed our understanding of the cosmos. On average, every star in the Milky Way hosts at least one planet, and roughly 1 in 5 Sun-like stars possesses an Earth-sized planet orbiting in the habitable zone. The mathematics becomes staggering when applied to our galaxy's scale. The Milky Way contains between 100 and 400 billion stars. If 20% of Sun-like stars host Earth-sized planets in habitable zones, that yields a minimum of 11 billion potentially habitable worlds in our galaxy alone. These aren't speculative projections based on wishful thinking, but statistical extrapolations from actual observations of thousands of planetary systems. We've transitioned from a universe where Earth might be unique to one where we know with certainty that billions of Earth-like worlds exist in regions where liquid water could flow. Yet despite this abundance, we've detected no confirmed technosignatures, no verified biosignatures in exoplanet atmospheres, no response to our radio transmissions into space. The Fermi paradox, which asks, "Where is everybody?" has intensified to an almost unbearable tension. With billions of potentially habitable worlds in our galaxy alone, each having existed for billions of years, we should see evidence of life everywhere we look. The galaxy should be teeming with civilizations at various stages of development, but the cosmos remains silent. This creates the most profound mystery in modern science. We know the raw materials for life are common, Earth-like planets orbiting in habitable zones around stable stars. The building blocks of organic chemistry exist throughout space. Water's abundant, yet we find nothing. Either life is extraordinarily rare despite favorable conditions being common, or intelligent life inevitably destroys itself, or advanced civilizations deliberately hide from detection, or we exist in some kind of cosmic isolation we don't yet understand. The silence in the face of such abundance has become the greatest mystery of all. Number 1. Phosphine in Venus's atmosphere. On September 14th, 2020, a team led by Professor Jane Greaves announced one of the most controversial and potentially revolutionary discoveries in the history of astrobiology. Using the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile, they detected phosphine gas in the clouds of Venus at an altitude between 53 and 61 kilometers above the scorching surface. The detection showed phosphine concentrations around 20 parts per billion, present in the only region of Venus where temperatures and pressures resemble Earth's surface conditions. What made this discovery extraordinary was that phosphine is incredibly difficult to produce through natural chemistry, yet it was present at concentrations far exceeding anything geological or photochemical processes could explain. Phosphine consists of one phosphorus atom bonded to 3 hydrogen atoms, and it shouldn't exist in Venus's atmosphere for more than seconds. The molecule is rapidly destroyed by sulfuric acid and ultraviolet radiation, yet it was being continuously replenished by some unknown source. Every known abiotic process has been examined and found incapable of producing phosphine at the detected levels. Scientists calculated that maintaining the observed concentrations would require production rates approximately 1 million times faster than any geological mechanism could achieve. On Earth, significant quantities of phosphine are produced by only 2 sources: industrial chemical processes and anaerobic bacteria living in oxygen-free environments where they use phosphine as part of their metabolism. The announcement triggered intense scientific debate that continues to this day. Subsequent analyses have questioned the original measurements, with some researchers arguing the spectral signature might be sulfur dioxide instead of phosphine, or that the detection was at the threshold of instrument sensitivity and could represent statistical noise. Other teams reanalyzed the data using different methodologies and confirmed phosphine's presence. Multiple follow-up observations using different telescopes have produced conflicting results. The scientific community remains genuinely divided, with peer-reviewed studies supporting both the detection and its refutation. What elevates this discovery beyond mere scientific controversy is its location. This isn't a distant exoplanet 120 light-years away that we can only study through atmospheric spectroscopy. This is Venus, our nearest planetary neighbor, a world we've studied with dozens of missions since the 1960s and long ago dismissed as utterly hostile to life. The planet's surface temperature reaches 900 degrees Fahrenheit, hot enough to melt lead. Its atmospheric pressure equals being 3,000 feet underwater on Earth. The clouds are composed of sulfuric acid. Venus seems like the last place in our solar system we should look for life, yet Venus wasn't always hellish. Scientific models suggest the planet may have possessed liquid water oceans for its first 2 to 3 billion years, potentially remaining habitable longer than Mars. If life evolved during that clement period, it could have retreated upward as the surface became uninhabitable, adapting to increasingly extreme conditions until only the cloud layer remained tolerable. At 53 to 61 kilometers altitude, Venus's atmosphere maintains temperatures around 30 degrees Celsius, and Earth normal pressure. Despite the sulfuric acid, some Earth bacteria called acidophiles thrive in equally corrosive environments. The clouds remain suspended, never falling to the hellish surface below, creating a permanent aerial habitat. The implications are staggering. If phosphine is confirmed and no abiotic source is found, it would represent our first verified detection of a biosignature beyond Earth, fundamentally transforming astrobiology from theoretical speculation to observational science. It would prove that life exists not just on one planet in our solar system, but on two, suggesting biology is not a cosmic accident, but an emergent property of chemistry that arises wherever conditions permit. The discovery would come from our neglected neighbor, the planet we'd written off as a dead world while obsessively searching Mars's frozen deserts and planning missions to distant ocean moons. The ongoing scientific debate itself reveals profound truths about how difficult it is to prove we found life, even when it might be floating in our neighbor's atmosphere. We've developed the technology to detect molecular signatures at planetary scales, but distinguishing between exotic chemistry and biology at that distance remains an immense challenge. The phosphine controversy demonstrates that definitive proof of extraterrestrial life may require not just detection, but multiple confirmations, exhaustive elimination of abiotic sources, and perhaps eventually direct sampling. The phosphine debate forces us to confront our assumptions about habitability and challenges our understanding of which worlds deserve serious astrobiological attention. For decades, we've focused on Mars and the icy moons of the outer solar system while ignoring the hellscape next door. If Venus harbors life in its clouds, it teaches us that the search for biology beyond Earth requires looking not just to distant stars, but reconsidering the worlds we thought we already understood. It suggests that life may be far more tenacious and adaptable than we imagined, capable of surviving in environments we dismissed as impossibly hostile. Most profoundly, it raises the possibility that the question of whether we're alone in the universe might be answered not by radio telescopes detecting alien civilizations or by drilling through Martian ice, but by atmospheric chemistry on a planet we've known about since ancient times, but never truly understood, teaching us that sometimes the most revolutionary discoveries come from looking with new eyes at what was always right in front of us. If you want to see more videos like this, click the video on screen now and make sure to subscribe.